Okay, welcome back. This is the second screencast for Chapter 4 on matrix algebra. So now we're still in section 4.1. We're going to introduce the notions of matrix addition and scalar multiplication. And if you remember how things go with vectors, you'll find this pretty straightforward. The way of adding matrices and the way of multiplying by a scalar is exactly the same way that you did it for vectors, right? To add vectors, you added the corresponding entries, and it's going to be exactly the same story for matrices. Um, so you want to add two matrices together. Well, the first thing is they've got to be the same size, right? Think about when you're dealing with vectors. It wouldn't make sense to add a two-dimensional vector to a three-dimensional vector. The two vectors have to belong to the same space. They have to have the same number of entries. And same thing for matrices. If I want to add two matrices together, they have to be the same size. And once I have two matrices of the same size, how do I add them together? I simply add the corresponding entries. So if A has entries Aij, B has entries Bij, then the sum is obtained by simply adding those numbers together. Here you see why this notation, this index notation, is quite useful. Writing A in terms of entries instead of writing Aij, rather than kind of writing this thing out in full. If I wanted to define A plus B, writing out my matrix in full, it would take up the whole page if I was trying to do it quite generally, right? So what does that mean in practice? Well, it means if I wanted to do, say, A plus B, I check, okay, so A is, what's the size of A? It's got 2 rows, 3 columns. A is a 2 by 3 matrix. B is a 2 by 3 matrix. They're both the same size, so I can add them. So 1, minus 2, 3, 0, minus 4, 2, minus 3, 0, 1, 0, minus 3, 2. And my rule says that the way I define this sum is I simply add the corresponding entries. So 1 plus minus 3 minus 2 plus 0, 3 plus 1, 0 plus 0, minus 4 plus minus 3, 2 plus 2. Okay, so I add the 1, 1 entry. So the 1, 1 entry for A is a 1. Right here, the 1, 1 entry for B is a minus 3, and adding those together gives me the 1, 1 entry for A plus B. Similarly, the 1, 2 entry for A minus 2, 1, 2 entry for B is a 0. Adding them together gives me the 1, 2 entry for the sum, and so on. So then, to simplify, I simply carry out these additions. Minus 2, 4, 0, minus 7, 4, and you'll notice that the result is the same size as the two matrices you put in. There's a third matrix C there. I could try to talk about addition involving the matrix C, but there's not much I can do, right? A plus C, B plus C, those are undefined. Right, because C is a 2 by 2 matrix, and so it does not make sense to add C to either A or B, right? If you try to sort of do A plus C, you'd look at those numbers in the third column, you know, this 3 and that 2, and you'd say, well, what do I add them to from the matrix C? I need a corresponding entry in the other matrix to add to those guys, and nothing is there. And so you simply just don't define that. But the only thing you could do is C. I guess you could add C to itself. You could do C plus C, and you could do that. And in fact, you can see what you would get. You would get, well, 1 plus 1, minus 2 minus 2, 2 plus 2, 4 plus 4. So you double everything. 1 plus 1 gives you 2. Minus 2 minus 2 gives you minus 4. 2 plus 2, 4. 4 plus 4 gives you 8. And you might guess that, you know, there should be some sort of operation, some scalar multiplication operation that would allow you to say that this is equal to 2 times C. And we'll see that indeed that is the case. We'll be there pretty soon. But we got to finish our discussion of addition first. So let's move forward. What sort of properties does this matrix addition have? I'm listing them all here. I'm not going to go through the proofs. We can do a couple of them if you're interested in. You can ask Jeff to do them in the tutorials if you want. The addition of matrices satisfies most of the properties that you expect it to satisfy. Okay, you have a commutative law telling you that the order in which you add your matrices does not matter. A plus B is the same thing as B plus A. If you want to extend the definition of addition to sums of 3 or more matrices, then you need to have an associative law. You need to know that it doesn't matter how you group those matrices together, you will always get the same answer, right? So this associative law is what tells you that simply writing A plus B plus C is unambiguous. Right. You can interpret that either as first doing A plus B and then C, or you could interpret it as doing B plus C and then adding A. You'll get the same answer either way. Okay. The zero matrix, as you might expect, the zero matrix is the matrix whose entries are all 0. Okay, so Aij equals 0 for each I and each j. The zero matrix, well, if you just look at the definition of matrix addition here, right, if B is the zero matrix, if all of the B's are equal to 0, then when I do A plus B, I'd be adding 0 to each of the entries for A, and I know that adding 0 does nothing. So adding the zero matrix doesn't do anything, right? So 0 acts as an identity element. Adding 0 doesn't do anything. So A plus 0 is equal to A no matter what the matrix A is. And you can define the negative of a matrix by simply flipping the sign of each entry in the matrix, and as you might expect, adding a matrix to its negative, everything cancels out and so you get 0. And one of the reasons that you want to define a negative is that once you've defined negatives, you can then define subtraction. So the way you define A minus B is you say, well, A minus B is the same thing as adding the negative of B to A. So A minus B is A plus the negative of B. This is how you define subtraction. Very much the same as you do when you're dealing with real numbers. And by the way, if you wanted to prove some of these, let's say you wanted to prove the commutative law. Let's say we want to do this guy, right? So if you wanted to write out a proof, and obviously I don't have room to write everything down, and I should be kind of trying to write things out in full sentences, but if I said, okay, let me let A equal to Aij, and let me let B equal to Bij, right? Then I'd say, well, A plus B, I know by definition, is Aij plus Bij. And the reason why the commutative law holds is that the commutative law holds for numbers, right? Aij plus Bij, each within the matrix, I'm adding numbers. I'm adding the ij entry from A to the ij entry from B. This is a sum of numbers. And I know that order of addition doesn't matter for real numbers, so Aij plus Bij is the same thing as Bij plus Aij. And then I simply reverse the definition of addition to say, well, this is, by definition, B plus A. Okay? And similar arguments can be used to establish the other properties here. Okay. All right. Let's do a computational example just to kind of play around with things, see how this works. So if I wanted to do A minus B, I would say, okay, that's the same thing as A plus minus B. You don't have to do it this way. You can simply, as you might expect, subtracting matrices means subtracting corresponding entries. But one of the ways to make it less likely that you're going to make a sign error, because each of these matrices has 6 entries, and that means 6 opportunities to mess up with a minus sign. You might want to actually sort of first switch the sign and then add. So if I want to form this matrix minus B, I have to go into the matrix B and I have to swap all of the signs. So I have a minus 1. So I start with 1, minus 1, 1, 0, 2, 4. That's B, but then I switch all the signs. So I get a minus 1. This becomes plus 1, minus 1. Well, minus 0 is still 0. Minus 2, minus 4. So I swap all the signs, and then I add. So 3 plus minus 1 gives me 2. Minus 1 plus 1 gives me a 0. 0 plus minus 1, minus 1. 2 plus 0, 0. 4 minus 2 is 2. Minus 5, minus 4 gives me minus 9. Oh, what happened here? That's not right, is it? 2 plus 0. 2 plus 0 is 2. It's not 0. Okay, so we've done the subtraction, a minus b. If I wanted to do a plus c, well, we've already gone over that. We add the corresponding entries. So maybe we'll just sort of jump ahead, add the entries. So 3 plus 1 minus 3, 0 plus 2, 2 plus 5, 4 plus 0, minus 5 plus 4, and that's going to give me 4 minus 4, 2, 7, 4, minus 1. If I wanted to do the last one, a plus b minus c, I might do it as, let's do it this way. Let's do it as a added to b minus c. So I'm going to do it like this. There are a number of ways that we could do this, but here's how I want to do it. I'm going to write down a, and then I'm going to do b minus c. So what is b minus c? 1 minus 1, minus 1 subtract minus 3, 1 minus 2, 0 minus 5, 2 minus 0, 4 minus 4. Okay? So this is b minus c. So I've done the entries of b and I subtracted off the entries for c. So that's going to give me 3 minus 1, 0, 2, 4, minus 5, added to 0, minus 4, minus 1, minus 5, 2, 0. So I add those together. Let me put it up here. So let's kind of wall things off. I'm going to get, so 3 plus 0, 3 minus 1 minus 4, minus 5, 0 minus 1, 2 minus 5 is minus 3, 4 plus 2 is 6, minus 5 plus 0, minus 5. Okay, so far so good. Let's talk, well, let's do one more example. I thought we were on scalar multiplication, getting ahead of myself. Okay, let's say I want to find this matrix X. How do I solve for X? Well, we know how this story goes. We've seen examples like this with vectors, with complex numbers. If this is A and this is B, right, so I have A plus X is equal to B, then I should say, well, I add minus A to both sides. Minus A plus X is equal to minus A plus B, so I add the same thing to both sides. And so I know that if I group things together here, those A's are going to cancel out. Minus A plus A gives me 0. Adding 0 to X just gives me X, so X is equal to B minus A. So X is going to be 5 minus 7, 0, minus 3, subtract 2, 4, minus 1, 3. And so I've got 5 minus 2 is 3. 7 minus 7 subtract 4, negative 11. 0 minus 1, make sure you get that double negative, plus 1. Minus 3 subtract 3, minus 6. That's your X. And if you want, you can go back and check that if you do add this matrix to 4 minus 1, 3, you end up with the matrix 5 minus 7, 0, minus 3. Right? As usual, there are ways of checking your work. Okay. Last up for this video, scalar multiplication. Again, defined exactly the way you expect. If you want to multiply a matrix by a scalar, you just multiply every entry in that matrix by that scalar. Right? So in almost all the problems that we're going to do, scalar means real number. We're working with matrices with real entries, so scalars are real numbers. And we know how this works, right? It's the same way we did scalar multiplication for vectors. So for example, if I wanted to do, let's say, 3 times the matrix minus 1, 2, 4, 0, I would say, well, it's 3 times minus 1, 3 times 2, 3 times 4, 3 times 0, minus 3, 6, 12, 0. Okay, so scalar multiplication is what you expect. You just multiply every entry in the matrix by that scalar. And scalar multiplication satisfies a lot of the properties you might expect scalar multiplication to satisfy. One thing you'll notice is, well, because you're just multiplying each entry in the matrix by a scalar, you're not changing the number of rows or columns, so scalar multiplication preserves the size of your matrix. And well, if you multiply by the scalar 0, then of course everything multiplied by 0 just becomes 0, and you end up with the 0 matrix, right? So multiplying A by 0 gives you 0. And also, if you start with a 0 matrix, it doesn't matter what scalar you multiply by, you're still going to have the 0 matrix. And you can turn that around, and you can say, well, if I had a product equal to 0, if I had, like k times a equals 0, then I conclude that either k is 0 or a is 0. Often where that comes in handy is you end up somewhere where you've concluded that, let's say, 2a equals 0, and then from there you can get rid of the 2 and say, well, then I must know that a equals 0. Scalar multiplication, as with vectors, satisfies distributive properties, and as with vectors there are two, because this plus sign here is matrix addition, right, as it is here and here. This plus sign here is addition in R, right? You're adding the scalars together. That's why there's two different distributive properties, because one is distribution over matrix addition, the other is distribution over scalar addition. And as usual, this second one is what allows you to group like terms, right? So this would tell you that, for example, if I had 3a plus 4a, that's 3 plus 4a, so I get 7a, as you would expect. Okay, and multiplying by 1 doesn't do anything, and if you want to multiply by one scalar and then another, that's the same as multiplying the scalars together and then multiplying by a, right? So these are all exactly the same properties for addition and scalar multiplication that we saw for vectors. And in fact, if you were kind of doing abstract linear algebra, you might say, well, that the set of all matrices of a particular size is what's called a vector space. It satisfies the same rules as algebra for vectors. So you say, well, this algebra is the same as vector algebra, and so you, in some ways, you can treat them as vectors, as a certain type of vectors. But that's not an approach that we take in this course. For us, vector spaces are generally going to be, vectors in Rn the way we've usually been thinking about them. Okay, that's it for matrices. We'll be looking at vectors again in the next few videos. Only this time we're going to be changing notation. We're going to be thinking of vectors as either row vectors or column vectors. So a vector will be either a 1 by n or an n by 1 matrix. So we'll be thinking of vectors as special types of matrices going forward from here, starting in the next video.